Hi, and welcome to Codex. Our speaker today is Dorsa from the St. Louis University. She is an expert on applied harmonic analysis, frame theory, phase retrieval, and functional analysis. Today, she'll tell us about frames and phase retrieval for vector bundles. Take away, Dorsa.
Thank you, Emily, and I want to thank the organizers for the invitation. It's great to give a talk in Codex seminar. Yes, as Emily said, I'm going to talk about frames and phase retrieval for vector bundles today. I'm going to talk about some results from these two papers that we had in recent years. One of them is stable phase retrieval and perturbation of frames, which is a collaboration with Dan Freeman and students. And another one that is frames and phase retrieval for vector bundles, which is a recent one. And it's again a work with Dan Freeman and Luva with undergraduate students at St. Louis University. So I think I should start with the definition of frames. We say a family of vector is a frame if there are constants A and B, upper and lower frame bounds, so that this inequality is satisfied. So what we are looking at here is I'm just taking the inner product of my vector V with the frame elements. And I'm going to bound it above and below by these two constants and the norm of my vector V. Another definition that I would want to define here at the beginning is the analysis operator. The analysis operator takes elements from the Hilbert space to the little L2, and it works in a way that when theta is applied to our vector V, I'm just looking at the frame coefficients in a sense, like just the inner product of V and Fi that I'm going to call the frame coefficients from now on. So this theta is taking just elements from H2 little L2. Okay, and I'm going to talk about how the recovery of vectors from linear measurements work out. So we are thinking if I have this frame coefficient information, if I have the given an image or image of a signal, let's say, under the analysis operator, or in other words, if I have the frame coefficients available to me, how can I reconstruct my vectors from these linear measurements? So if I'm applying this linear operator, which is the combination of theta is analysis operator and theta star is the synthesis operator. So if I apply this linear operator to my frame coefficients, what happens is that I can just take the V back. So this is the reconstruction that happens by just applying this linear operator. Everything works out nicely, and I can take my vector back by only knowing the frame coefficients. But what happens is that this involves inverting a matrix, and it's often computationally expensive, but there are some fast algorithms that do the job, and we can get this recovery from just the linear, by just applying this linear operator. In the definition of frames, we say that we have A and B, the upper and lower frame bound. But if you take those two equal to 1, you will get into the definition of a parsable frame, which is just for us to satisfy this equality here. But what is interesting about parsable frames and very strong about parsable frames is the ability of reconstructing just from this. So if I have the parsable frame, I can recover any vector by just looking at the frame coefficients multiplied by my Fi, and this summation is going to recover my V for us. So this is going to be we can think of it in a way that the reconstruction formula for parsable frame always holds if I only have the parsable frame here with any vector in my Hilbert space. there is a connection that I want to create here or make here, which is the connection of a parsable frames with the projections of orthonormal basis. So the proposition here says that if I start with two Hilbert spaces, H and K, and if I pick elements in the larger Hilbert space, and I'm using the orthogonal projections, if I look at the orthogonal projections applied to this EIs that are in my K, then this is going to give me a parsable frame. So in a sense, I can think of this example that if you have, let's say, a 3, in R3, if you have an orthonormal basis EI, and you are using orthogonal projections to project it onto this plane that passes through the origin, this is going to create this, like, green vectors is going to be a parsable frame for me. So this nice property is giving me a lot of tools here that I can go from just the orthonormal basis projected, and now in a lower dimension, I have a nice parsable frame. Now, how are we going to move to vector bundles? And we are thinking, instead of using a single fixed Hilbert space, I'm going to consider a vector bundle over a whole manifold. And there are certain things I want to set up at the beginning. First of all, what is a vector bundle? If I get two manifolds, a rank n vector bundle would be this continuous map pi that goes from E to M. And it's going to be in a way that if I take any element in my manifold, pi inverse of x, which we are called fibers, it has the structure of an n-dimensional vector space. If you look at this picture, we're taking this pi, which is our vector bundle. It goes from E to M. And if you think about it here, if I'm looking at M and take this X on M, there is pi inverse, there is this fiber correspondence to this point. And this E is going to be the disjoint union of these fibers. And in another example, if you think about a sphere and take an element on this manifold, pi inverse of x, or the fiber, is going to be a plane that includes this x, and it's going to be tangent to our sphere. And we're considering that each fiber is a Hilbert space, and the inner product is going to be continuously over the manifold. Another thing that we need to define at the beginning is an idea of a section of a vector bundle. So section of a vector bundle is going to be this continuous map F that goes from M to E, such that if I take any element from my manifold, the F of X is going to be a vector on this fiber. So we can think of this like if I have this point X, then this F of X is going to be a vector that is on this fiber, pi inverse of X, and it's going to be just lying here. And if you want to think about it in another way, the function, this continuous map that takes M to E, works out really nicely, and it's going to create a vector in my fiber. And this is another definition that we need. Now I'm going to think about moving parsable frames on these vector bundles. So instead of just looking at a fixed Hilbert space, we're extending this to a parsable frame, in a moving parsable frame, over a vector bundle. So there are some work done in this area. There is a paper by Ballas, Needham, and Schankweiler, a very recent one, and some work by Dan Freeman and other collaborators in different years, and the works by Kuchman, which studies, these papers study the mathematics behind this. And I'm going to define what moving parsable frame is. And a moving parsable frame I'm looking for a case when I'm calling this Fi's my moving parsable frame. So I'm looking at these sections, smooth sections over my vector bundle that if I'm looking at the K of these sections, smooth sections, I call them moving parsable frame. If for any x that I take on my manifold M, Fi of x would be a parsable frame for the fiber, the pi inverse of x here. Or in other words, what we talked about at the beginning about the the parsable frames and the reconstruction formula for the parsable frames is that now for any vector that I pick in my fiber, the reconstruction formula holds. So you can think of it as take any vector on the manifold, the reconstruction formula is going to recover the V back by only looking at the coefficients or the frame coefficients of V with Fi of x. So this is what we will use and study with moving, the idea of moving parsable frame, and we're going to go to details with that. So first of all, and one question that we can ask is that why are we looking at moving parsable frames and not moving bases? So one interesting thing is that if I'm, let's say, considering a sphere and I'm taking orthonormal basis, then at each point, I can create a moving parsable frame on the tangent space. But this is not the case for moving bases. So many vector bundles don't have a moving basis, but every vector bundle has a moving parsable frame. So this is an important thing for us. And this goes back to a so-called hairy ball theorem, which states that if n is an even number, let's say here S2 that we have, there does not exist an over zero vector field. So in other words, by this theorem, it says that we might lose some vectors and we won't have enough to be able to create a basis for us. So in S2, we cannot have a moving basis for its tangent space. And so if you look at this picture, it's like a cartoon of what happens in the hairy ball theorem, is that at some point on the sphere, things get weird and it's just going to project to 0, and you might not be able to have a moving basis. And then in this picture, I tried to show what happens when you have when you're taking an orthonormal basis and you're projecting that on this subspace or in this tangent space, then you can see that this is forming a moving parsable frame for us at each point. But the takeaway here is that moving parsable frame always exists, in contrast to moving bases that might not exist at some point. And there are some results that are very interesting and important here to mention is that a moving parsable frame of K sections, we can lift it to a moving orthonormal basis of a rank N vector bundle. So if you're taking two, there's this theorem that says if you're taking two vector bundles, pi1 and pi2, let's say pi1 is rank N vector bundle, and we are taking the moving parsable frame in there, Fi's in there, and say that I have pi2, which is a rank K minus N vector bundle with another moving parsable frame. Then if I look at the direct sum of these two, this is going to be a moving orthonormal basis for a vector bundle that goes from pi1, that is like pi1 and pi2 combined together. So this is saying that if I have two moving parsable frames, in a sense, a direct sum of those moving parsable frames is going to be also a moving orthonormal basis for our vector bundle. And in the complementary to that, there is a theorem by Ballas, Needham, and Scheinweiler, which says that in order to create a parsable frame of size n, I need to have at least, this needs to be at least the size of the dimension of our manifold plus the rank of our vector bundle. And this is really interesting to see, like in order to create the parsable frame of a certain size, we need to at least have this much of information. And another thing that I want to mention here is that for a moving orthonormal basis, we are looking at this fibers as a subspace of our HK. And we are going to use a parsable frame to measure a distance between the vectors and different fibers. So that's going to give us a great tool to say how far away the vectors and different fibers would be from each other. So in order to find this distance, we are looking at taking elements, taking two vectors, one in fiber pi inverse of x and another one in another fiber for any two vectors x and y in our manifold. Then we are saying that if I'm looking at the distance of these two, this is going to be this much. So it's going to be just the inner product or the frame coefficient of my v of x with fi of x, and subtracting that from the frame coefficients for uy and fi of y. So in this way, I can have some control over saying that how much two vectors on a fiber and two different fibers would be and how far away they are from each other. And another thing we have is that if fi is a moving parsable frame, this equation would correspond to the distance on the fiber pi inverse of x when you have the x and y equal to each other. So this way we're finding the distance between the fibers, and that gives us another tool to say that, okay, if I want some vector to be close enough to my vector, this is how I'm going to define the distance and say if it's close enough or not. The question that we would like to ask here is that given a vector bundle and a moving parsable frame, can we approximate a section of f from sampled frame coefficients? So we are going to think about it in other words. If I have sampling points xj's, we can approximate, or the question is, can we approximate f from only having these values, like the frame coefficient of f evaluated at those sampling points with the fi of xj's? This would mean the following things. We're going to decide where to put these sampling points or where to place these sampling points across the manifold. And we are going to develop functions that approximates the sections locally close to the sampling points and close in the meaning of the distance that we talked about. And having these local approximations, we're going to glue these local approximations together to find a global approximation. And we're going to use the partition of unity for that. So we can say, can we approximate every section from finitely many sampling points? Can I do that? Well, the question is no, or sorry, the answer is no. I can think of this in a way that if I am given a finite set, xj's, these sampling points, we can choose a section, f, that can be really large, but the value at that sampling point would be 0. So technically, it's not going to give me any information to be able to approximate it nicely. So in order to fix that, we are only, or not deal with this scenario, we are only considering the sections with a given bound on their modulus of continuity. So I'm going to use the modulus of continuity to say that, well, I don't want it to be large, really large, and want to have control over it. So modulus of uniform continuity says that if I'm looking at this for a section f, is that if I'm looking at this function omega, the omega of delta would be the supremum of f of y, the distance of f of y and f of x. So take any points on the manifold, you're looking at the supremum of this distance of these two vectors from each other. And this is going to restrict how much a section can change between different sampling points. So we don't want that to be really far away from, we want to have kind of a control to look at nearby locations, like xj's should be a good approximation for my f of x in general, or in the end. So how are we going to do these approximation? First of all, by putting this bound on the modulus of continuity, we are guaranteeing that if x is sufficiently close to a sampling point xj, then the frame coefficients can be a good approximation. Or the frame coefficients for f of x can be approximated by the frame coefficients of f of xj. In other words, I'm looking at a scenario where I'm only I want to have like approximate f of x with what I call local approximations, meaning that I'm going to get really close by looking at the nearby sampling points. And I'm going to look at this, which the whole thing is on the fiber, looking at approximating f of x with these local approximations. But how do we get an estimate for this? The idea that we had for getting a good estimation for this local approximation is the idea of using perturbation. So I'm going to talk a little bit about perturbation and how things how things change when I'm looking at perturbing a frame. So we say if I have a family of vectors gi, I'm saying that this is the epsilon perturbation of my frame if when I'm looking at the norm difference of fi and gi, it's bounded by this epsilon. And what does that mean? This perturbation in application means that each f of I can be, each frame can be looked at, can be think of as a sensor that is used to measure a signal v, and perturbing this, like going from fi to gi, corresponds to making small errors in setting up the sensor for the experiment. So this can, like, this little change in our frame it's what's called as epsilon perturbation of our frame. Now there are some results that says that, okay, now we have this set of vector that is a perturbation of our frame. This theorem by Christensen guarantees that if I'm looking at this perturb vector or set of vectors, this is going to be a frame, but the upper bound and lower bound is going to be slightly different than the original frame fi. And what we were able to kind of connect here is that if I start with two frames that are, one of them is a perturbation of the other one, and take b for the upper bound of the original, or let's say fi, then for any u and v that you take in your Hilbert space, the following holds. So what is this saying is that I'm looking at the inner product of the inner product of u and fi's, and this is the frame coefficient that I have between u and fi, and a frame coefficient for between v and gi. If I look at this difference, it's going to be bounded above by this term, which depends on only the upper bound of f and the how far away u and v are from each other, plus the epsilon of the perturbation. But how are we going to use this information to get back to our approximation part? Our goal is to use the sampled values to approximate the vector f of x. But what is f of x? Since we said that fi is a parsable frame, we have this reconstruction formula. So basically, I'm looking to use these sampled value to approximate f of x, which is in the following form. And the lemma gives me that if I have x and xj's, like the sampling points, if they are close enough to x, then what I have, the local approximations, is going to be a good approximation for f of x. So with this idea of perturbation, we are guaranteeing that as long as x is close to, or xj is close to x, this will give us a good approximation, or this local approximation would be a good one to choose for approximating f of x. Now, at some point in the process, I said that our idea is to use this local approximations and glue them together in a way to get the global approximation. But how does this process work? So the idea, the goal we have is to approximate f of x from these local approximations. And I'm going to use the global use the partition of unity to glue them together. And how does this partition of unity work? Is that it's in a sense weighting or adding the weights to our process. So it's saying if the approximation, if your xj is far away, you are giving it less weight. And if it's a good approximation, if it's close by, you'll give it a larger value. So I'm looking at the psi of beta, the partition of unity, which is with all of them adds up to 1, and they're going to give different support in different locations. So the theorem, like combining all those local approximation to global approximation in combination with using the partition of unity, it tells me that if I'm looking at how far away f of x is with this one, or like I'm approximating f of x using this local approximation, this works and it works nicely. So if you think about this psi j of x is going to give me, again, like weighting it in a way that it gives larger number when we are close, so that this approximation in general would be a good approximation. It's within an epsilon. All right, so this was one of our results. But now we could ask different questions that are going to get to, which is that can we always do this, and a lot of other questions we can ask here. Okay, so I'm going to move to phase retrieval for vector bundles. After thinking about vector bundles, we were deciding to see, okay, what's going to happen for the phase retrieval case if we are now on the vector bundle, and what does that look like in this setting. I'm going to tell you a little bit about what phase retrieval is. So phase retrieval is the problem that was in physics and in optics application, such as X-ray crystallography. They wanted to know a little bit more about the structure of the sample. And the way it works is that they hit the sample with an X-ray source, and it gets diffracted into different patterns. And now the question is, when you have this information with these diffraction patterns, how can you recover some information and say something about the structure of this sample? And in our in a way that what we want to think of is that phase retrieval is the problem that now the information that I have and I want to recover V from, it's only the magnitude of these frame coefficients. So I only have the magnitude here, and with this, again, I'm going to go back and try to find V. In a sense, if I'm like applying this theta and I have theta V now as my information, with phase retrieval, I am now having less information. So I don't even know if it's positive or negative in different parts. And the question is, what would be this recovery map so that I go from only the magnitudes of theta V to be able to recover V? And in terms of the definition, what we're saying is phase retrieval is that take any two elements, any two vectors x and y in H. We say our frame does phase retrieval if when I have the magnitude of the frame coefficients of V with my frame and U with my frame, then there is a lambda such that V is equal to lambda U, the lambda modulus 1. So in the real case, you can just think about it as V is equal to plus or minus U. In other words, or another way to say the same thing is that if you're considering the equivalence relation on H, given by V is equivalent to lambda V, a frame does phase retrieval for a Hilbert space if whenever I'm taking, whenever for any two vectors V and U, if I have this satisfied, then I can say V is equivalent to U. So this is another way to say that a frame does phase retrieval. So I'm looking at this equivalence relation. I'm saying that if V is equivalent to U, is saying that we have phase retrieval. Now, how does things work on vector bundle? When I'm talking about vector bundle, we have this property that if Fi does phase retrieval on a vector bundle, we can say that Fi does phase retrieval for a vector bundle if for any point that I pick on my manifold, Fi of x would do phase retrieval on the fiber. So this is one relationship that we have. In other words, we're saying that if you are thinking of sections F and G on your vector bundle, we say that F is equivalent to G if for any point x on the manifold, F of x is equivalent to G of x. And we say that phase retrieval for a section F is about recovering this equivalence class now. So if you think about the equivalence class of F on this M, you're thinking of basically recovering this equivalence class from the information that we have, which is just the magnitude of our F of x with Fi of x. So this is a little bit of a difference between this one and the normal or the other phase retrieval case, and that we are now recovering the equivalence class by just knowing the magnitudes. And another question that we can ask here is that how does the stability work for this recovery? So whenever we have this phase retrieval, we're asking the question of how does the stability work? So in the general phase retrieval, we're saying that a frame does C-stable phase retrieval if the recovery of my vector from this magnitudes is C-Lipschitz. In other words, if I'm looking at the minimum for any V and U, if I'm looking at the minimum of the distance of V minus lambda U, this is going to be bounded above by constant C times how far away this frame, the magnitude of these frame coefficients would be from each other. And another quick note here is that the recovery of this vector from the frame coefficients is frame coefficients like the theta v is 1 over square root of a Lipschitz, in the sense that if our frame does C-stable phase retrieval, then C needs to be at least 1 over square root of a. And what do we know about stable phase retrieval and phase retrieval? A theorem by Bandera, Cahill, and Dustin and Nelson, and another result by Balan and Wang, says that a frame for a finite dimensional Hilbert space does phase retrieval if and only if it does stable phase retrieval. And this works in finite dimensions. We have this nice if and only if property. So as long as I have C-stable phase retrieval, it does phase retrieval as well, or the other way around. And what we want to, and another thing about stability is that what would happen if I'm perturbing my frame a little bit. So with respect to perturbation, there is this theorem by Balan, which says that if I'm looking at frames of dimension m, if I'm perturbing this, which does see stable phase retrieval, if I'm looking at the perturb frame, GI, this is going to be also a frame which does 2C stable phase retrieval. And what we were able to show is that we can remove this condition of the dimensionality, and we can say for any frame in finite dimensional Hilbert space, the perturbation of that would do phase retrieval, stable phase retrieval as well, with a different constant. And well, going back to the moving parsable frame and the idea of that, we were able to show that for vector bundles, if I start with a moving parsable frame for a vector bundle, then this does phase retrieval if and only if there is a constant such that for any point of my manifold, Fi of x does C-stable phase retrieval for the fiber as well. So this is one result that we had in this situation. Okay, but going back to the phase retrieval part, how can we recover a section of a vector bundle from finitely many samples? Now, my question is, in other words, I want to say that how do I want to recover my equivalence class when the only information I have is the magnitude of these frame coefficients when f is evaluated at those sampling points, or for f of those sampling points. What is the problem here? The problem is that this equivalence class is not a vector. And we cannot use, so in the previous part, when we had a vector, we used the partition of unity, and we glued the local approximations together to get a global approximation. But here, this is our problem. This is not a vector anymore, so we need another tool to get the results for this version. A way to solve it is that we can identify an equivalence class with a rank 1 operator. So the way this is going to work is that so if you think about it, we are talking about phase retrieval. We are looking at the recovering of our vector. When I have this condition, I want to say that v is equal to lambda u for some lambda. By Hilbert-Schmidt, the following equality holds. And if I do some little calculation here, this shows me that I can say if I does phase retrieval, if and only if I look at this capital F disjoint operator, which goes from H to H, when the rank of F is between 1 and 2, now I can say the inner product of F with Fi star is non-zero for some I. And in other words, my point here is that if I'm looking at recovering this equivalence class, would be equivalent to recovering this self-adjoint rank 1 operator where f of x is like just the fx star, which is a rank 1 operator on the fiber. So this solves this problem, and we're going to use that capital F to do the job for us. And when we're doing phase retrieval for samples, we're assuming that we can do phase retrieval for each of the sampled fibers. Now, the question that we are going to ask is that how can we combine the samples to approximately do phase retrieval over the whole vector bundle? In other words, I want to say that if I am looking at sampling points xj's, our goal is to approximate a rank 1 positive operator f from the values f of xj's. So which we showed that this is equivalent to recovering this equivalence class. And one tool that we used before was using the partition of unity. But when I'm using partition of unity to sum the collection of rank 1 positive operators, I might get a positive operator with a rank greater than 1, so a lot larger. So I would not have a control over that. And in order to think another way to do this is that if I'm now combining collection of close rank 1 operators, positive operators, then what I get, the resulting operator, would be close by, and it will be still having a rank 1 operator. So I'm just going to think about just the collection of sufficiently close rank 1 operators, combining them, and using that to approximate my function. But how are we going to do this? We're taking the let's say R1 of G is a positive rank 1 operator, such that lambda 1 is the largest eigenvalue of this operator. And the corresponding eigenspace is also contained, like let's say R1 of G, the eigenspace of R1 of G is also contained in the eigenspace for G. So with that, I can think of now R1 of G, positive operator, rank 1 operator, and with a certain lambda 1. And I know that in order to guarantee that R1 is unique, or how do we know that the R1 is unique on this K, in general, we can say if I have a K that's a compact set of operators, and I don't have repeated lambdas, like lambda 1 of T is bigger than lambda of T, then R1 is going to be unique on this K, and it is uniformly continuous. So this will guarantee that it will work nicely. And another piece of information that I have is that I need to have another function here, tie of gamma, let's say, which is an increasing and smooth function, such that it gets the value of 0 for t's being in a certain interval, and it gets the value of t for t in another interval from 2 gamma to infinity. So the next one is just the theorem that we have. I know it's a little bit too much, but what I want you to look at is that I gave you all the components of this part, which R1 is what we defined in previously, and you can think of this as the G we had in the previous slide. The eigenspace corresponding to the largest eigenvalue of this is one-dimensional. And in order to approximate f of x, this will do a job that I'm going to look at the norm of this, which is a rank 1 operator, multiplied by the partition of unity. So it gives a good approximation for that. And this tie of gamma is also weighting it in a way that gives more values when it's closer, and smaller value when it's further away, so that this difference would be nice and controllable, and f of x would be a good approximation. In other words, this term is continuously moving rank 1 operator, and it's uniformly approximating f of x within an epsilon. So this was this was the result that we had, that we could like kind of answer the questions that we asked before. All right, another last thing that I want to talk about is the characterization of frames which do phase retrieval. So what we know is that a frame satisfies the complement property. There's this nice property called complement property, which says that if I have, if any time I set my frame into 2 parts, then one of those parts should span the space. And there is this theorem by Balan, Casazza, and Edidin, which says that in the real case, complement property is equivalent to doing phase retrieval. And in general, in Hilbert space, if a frame does phase retrieval, then it satisfies complement property as well. What we know is that as a consequence of this, in Rn, we need to have at least 2n minus 1 vectors to do phase retrieval. And in the complex case, it's 4n minus 4, and it's not sharp. Now we wanted to think about what those numbers would look like in the phase retrieval and vector bundle case. So if I'm starting with fi of 2n of the size 2n minus 1, and if I start with this moving parsable frame, I know that it does phase retrieval if and only if every n element subset is a moving basis. So this is one condition that I need to have. Every n element of that is a moving basis of the vector bundle. And a real rank n vector bundle has a moving parsable frame of 2n minus 1 vectors, which does phase retrieval, if and only if the the vector bundle has a moving basis. In a toy example of a Mobius strip, since in Mobius strip the manifold is non-orientable, then the tangent space have certain properties. The tangent space does not have a moving basis of 3 vectors. The tangent space does not have a moving equinorm parsable frame of 3 vectors, but it has a moving parsable frame of 3 vectors, and it does not have a moving parsable frame of 3 vectors, which does phase retrieval. So I'm going to give you an example of a Mobius strip that has a moving parsable frame of 3 vectors. So if you take 3 vectors, and this is like the Mobius strip, which goes into, we only have 2 options of 2 directions. If I'm starting with F1, F2, and F3 as a point here, then as it's moving along the way, F3 gets larger in the direction of F2, and F1 stays in the same place. And moving a little bit up, the F2 goes on the other direction, and F3 is still in the same place. And as it gets to the top, F3 projects back to the point or 0, and the F2 would be in the opposite direction. So remember that this is only an example of a moving parsable frame of 3 vectors, and it really badly fails phase retrieval here. You can see, like, if you take it into 2 parts, complement property fails immediately. Now with this, we know that there is, we do not have a moving parsable frame of 3 vectors, which is phase retrieval. However, we were able to find moving parsable frame of 4 vectors, which does phase retrieval. And an example of that would be kind of the same with the 3 or 4 vectors here, that you start with F4 being the 0 vector, and then F1, F2, and F3. And I'm moving into three steps. The first step, F2 projects to 0, and F4 gets larger in the same direction, in this direction of a previous F2. Then in the next section, basically what happens is that this F2 is going to replace the F3 vector that was there, and F3 gets to 0. And in the last section, what happens is that you can see F4 is again projected back to 0. And if you compare the bottom one to the top one, what happens is that F2 and F3 are flipped and everything stays the same. And that makes sense for the opposite direction of the Mobius strip. So we were able to find moving parsable frame of 4 vectors, which does phase retrieval here. However, there are certain things that we want to mention, that if I have Mn to be an n-dimensional manifold, we can immerse Mn to R2n minus 1. And we are choosing a parsable frame of 2 times 2n minus 1, which is 4n minus 3, which does phase retrieval, and projecting this parsable frame onto the tangent space is going to give us a moving parsable frame of 4n minus 3 vectors, which does phase retrieval in the tangent space. And an example of that is that there is a moving parsable frame of 5 vectors for the tangent space of S2, which does phase retrieval. Now, the question that we would like to ask is, how can we build a moving parsable frame for vector bundles which do phase retrieval and have some additional nice properties? And in particular, those properties that we have in mind, let's look at an example of a Mobius strip. It has a finite unit norm type frame for its tangent space. However, it does not have unit norm type frames of 4 vectors in its tangent space, which does phase retrieval. And the Mobius strip does have, and if you think about 5 vectors using the Mobius strip, you can do the job, and it does phase retrieval. So those were the questions that we would like to ask. And with this, I think I'm gonna stop here, and thank you.
All right, let's smash that reaction button.